Did you know that not all energy you use is actually converted into useful work? In this experiment, we are going to test a mini horizontal axis Pelton turbine to test its efficiency. This concept applies to water turbines, which are widely used for irrigation and electricity generation. Water turbines are part of the renewable energy system, which utilize natural resources such as flowing water.
In this experiment, a Pelton turbine is used. This turbine allows for high-velocity water flow with low discharge, which is suitable for laboratory experiments. Its simple design is also perfect for observation of energy conversion.
The performance of the turbine is analyzed using different physical concepts. A Pelton turbine is an impulse turbine that converts water's potential energy into kinetic energy. It works efficiently at high head and low flow rates due to high-speed water jets striking blades called a runner. The runner has a split bucket shape, allowing the water to be deflected effectively while reducing side forces. With this design, Pelton turbines typically achieve a hydraulic efficiency of about 85% to 90%. Flow rate describes how much water flows through the system over time. Potential energy comes from the height of the weight, while kinetic energy comes from its motion of the turbine. These energies are then converted into mechanical energy when the water hits the turbine. Power shows how fast the energy is transferred, and efficiency indicates how much of the input energy is successfully converted into useful output.
The turbine consists of 12 buckets, each with a width of 6 centimeters, attached to a metal disc with a diameter of 13.5 centimeters. A shaft with a diameter of 1.5 centimeters connects the turbine to a pulley system. The frame is made of slotted angle steel with a length of 100 centimeters and a width of 80 centimeters. All components are connected using bolts and nuts to ensure stability. A pulley is placed at a height of 135 centimeters and is used to lift loads. The turbine is enclosed in a transparent acrylic box to prevent water splashes. Water is supplied through a hose connected to a faucet and directed using a jet spray nozzle. The nozzle is aimed at the center of the bucket to maximize energy transfer. The bucket shape is designed to split and reverse the water flow, improving efficiency.
To determine the efficiency of the turbine, an experiment was conducted by lifting different loads. 3 loads were used: 150 grams, 250 grams, and 350 grams. Each test was repeated 3 times to ensure accuracy. When the jet spray releases water, it hits the turbine's buckets and causes the turbine to rotate. This rotation is transferred to a pulley system connected to the turbine. As the pulley rotates, a rope attached to it winds up, lifting the load upwards.
To evaluate the efficiency of the system, 2 main quantities are needed: the kinetic energy of the water as the input and the potential energy of the load as the output. The potential energy of the load is determined based on its mass and the height it is lifted. Meanwhile, the kinetic energy of the water cannot be measured directly in terms of mass during the experiment. Therefore, it is estimated using the flow rate of the water and its velocity. The flow rate is obtained from the volume of water passing through the jet spray over a certain period of time. The time considered is from when the water starts flowing until the load reaches the top. To determine the velocity of the water, a separate test was conducted using projectile motion principles. The hose was positioned horizontally at the height of 1 meter above the ground. When the water was released, the horizontal distance traveled by the water was measured. From this setup, the time it takes for the water to fall to the ground can be determined based on its vertical motion. Using this time and the measured horizontal distance, the velocity of the water flow can be estimated.
Next, we calculate the speed of the water using the speed formula. Here, the value of time, or t, was obtained from the previous calculation using the free fall equation, which is 0.452 seconds. From the experiment, the horizontal distance, or x, is 6.12 meters. Now, we substitute the values into the speed formula. So, the speed of the water flow in this experiment is 13.6 meters per second.
Once the input and output energies are obtained, the efficiency of the turbine can be calculated by comparing the useful output energy to the input energy from the water.
In addition, the power of this system is also analyzed by comparing how much energy is transferred over time, both for the water input and the load output. To further understand the system, the rotational motion of the turbine is also considered. The relationship between linear motion and rotational motion is used to estimate how fast the turbine and the pulleys are spinning. The angular velocity of the pulley connected to the load, the pulley attached to the turbine, and the turbine itself are analyzed. These values are then compared with the rotational speed estimated from the water flow.
This table shows the time required for the load to be lifted to a height of 135 centimeters. After conducting the experiment 3 times for each load, we obtained data for the kinetic energy of the water and the potential energy of the load. The measured water flow rate was approximately 0.11 liters per second, with a water velocity of about 13.6 meters per second. The turbine's angular speed ranged from 64.4 to 190 revolutions per minute. However, the turbine speed was only about 6.2% to 18.4% of the water speed.
The comparison between input power and output power is shown in this table. From this data, we can see how much energy is transferred from the water to the load for each variation. This graph shows the relationship between the kinetic energy of the water and the potential energy of the load. It illustrates how the input energy is not fully converted into useful output energy. The efficiency of the turbine ranges from 5.29% to 8.82%. The highest efficiency was achieved when using the 250-gram load. This load also produced the highest output power.
Compared to theoretical or reference values, the efficiency is relatively low. This is mainly caused by friction in moving components such as the pulley and the turbine. Not all kinetic energy from the water is used to lift the load, as some of it is lost to overcome friction or is converted into heat. In addition, corrosion in the smaller pulley can also reduce performance. Another factor is the rope occasional tangling during the experiment, which slows down the rotation of the turbine and increases the lifting time.
Besides technical factors, turbine efficiency is also influenced by the water flow conditions. Higher water flow velocity can increase the turbine's RPM, resulting in greater power and efficiency. Future experiments can vary the water flow velocity and use a wider range of loads to determine the optimum condition for maximum efficiency.
To improve the system, friction should be minimized. This can be done by applying lubrication to the pulley and turbine components. Using non-corroded pulleys can also help improve performance. In addition, a guiding mechanism can be added to ensure that the rope winds neatly and does not tangle during operation.
In conclusion, the efficiency test of the Pelton turbine was successfully conducted using 3 different loads. The results show that the turbine efficiency ranged from 5.29% to 8.82%. The highest efficiency and output power were achieved with the 250-gram load, indicating that this load provided the most optimal operating condition for the system. Future experiments can vary water flow and load to determine the optimum condition for maximum turbine efficiency. So, did you know how efficient a small-scale Pelton turbine can be? Through this experiment, we found that not all energy can be converted into useful work. Thank you for watching and see you in our next experiment.